Hey everyone, we're back, and today we're going to talk about a relationship between force and velocity in a magnetic field that'll bring back some fond memories from the fall semester, I hope. So let's jump right in by having a magnetic field coming out of the board or out of your screen to begin our discussion. So there's our magnetic field coming out of the screen. The dots, of course, representing a vector coming out of the screen or out of the board or out of the page. And that's exactly what we've got. So this would be like a giant horseshoe magnet with its north pole back behind the screen and the south pole of that horseshoe magnet where you're sitting. So there's our charged particle, a positively charged particle as indicated by the plus sign. And that charged particle is moving in our field, which means it will feel a force. Let's indicate the direction of its motion with that nice little green arrow right there. That indicates the direction of velocity, so I'll label it with a V. And let's take a moment and think about what is the direction of the force that this positively charged particle feels in this magnetic field coming out of the page as the particle moves left to right as shown. If we apply the first right-hand rule, which I'll call RHR number 1, that rule can tell us the direction of that force. Take a moment and try to figure out what that direction is. Hope you've given it a little bit of thought. Using that first right-hand rule, you can figure out which way the force on that would be. Fingers coming out of the board, thumb to the right, looking at your right hand, your palm would be facing down towards the bottom of your screen. So there you have it, a force down towards the bottom of the page. Now, as we know, the force, the velocity, and the magnetic field are always mutually perpendicular, which means the force is always perpendicular to the velocity. If we know Q, and we know V, and we know B, we know the magnitude of that force. But we're not going to worry about the numbers right now. Let's just think about the implication of the direction of the force, the velocity, and the magnetic field in this situation. Hopefully this brings to mind some thoughts from back in the fall semester. We have a force that's perpendicular to a velocity. Is that force speeding it up or slowing it down? When forces act on objects, we know that they can accelerate that object, and yet we should ask ourselves, is the force that's perpendicular to the velocity, is it speeding it up or slowing it down? Well, to answer that discussion, or that question, maybe we should think about an equation, remember, from back in the fall semester. We thought about an equation that tells us when force is acting on something while it's moving, we can decide whether it's speeding up or slowing down by analyzing the work. And we remember that the work is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the displacement. Now, in this case, we don't really know about the displacement, but we know that the angle of the displacement and the angle of velocity are always the same. For any given instant in time, if something is moving in a direction, it's also displacing in that same direction, moving with a velocity in the same direction that it's displacing at any given instant in time. And we also know that since magnetic forces are mutually perpendicular with the velocity and B, that theta is 90 degrees and the work is always going to equal 0. So is it speeding up or slowing down? No, it's doing neither of those things, but it is accelerating. So hopefully you remember from September or November maybe, what does it mean to accelerate without speeding up or slowing down? Hope you gave that a little thought. You know that to accelerate without speeding up or slowing down means to change the direction of your velocity. And of course, that's exactly what's going to happen to our orange charged particle. Its velocity will change direction because of the force shown in red as it moves left to right and feels a force straight down. So let's imagine what that particle's velocity will look like in just a moment or so. I've just drawn for you in yellow what that orange particle is going to look like a little while from now. It will have moved off of the path that it was previously following and will now be moving on a path down here. It will have moved in a curved path from its original direction, shown here, to its new direction, shown lower in yellow. So now we see our yellow particle with its new velocity in its new direction, and we want to ask ourselves, what's the direction of the force on that yellow particle? Well, we get to use the first right-hand rule again, so take a moment and do that, and I'll be back in a few seconds to tell you if you're right. Now's when you should be thinking about it, by the way. I hope you've got it. So I hope you figured that one out. You notice if we use our first right-hand rule, now my thumb is pointed at around 4 o'clock, 4:30 on your clock. My fingers, of course, are still out of the page, and my palm is pointed down at like 7:30. If we're looking at a clock, the force and the velocity are still mutually perpendicular with the magnetic field, and you'll notice that the object, instead of moving in the line that it was directed when it was shown in orange, it's now moving in a new direction where it's shown in yellow. And I hope all of this brings to mind something very familiar from back in the fall. What we see here is circular motion. When the force is perpendicular to the velocity, as it is every step of the way for this charged particle moving in a magnetic field, it moves, of course, not in a straight line, neither speeding up nor slowing down, but instead it moves in a circle. And there, very roughly drawn, is the circle it would be moving in. We notice the center of that circle is where the forces are pointing at. And again, very roughly drawn center of the circle. But of course, the forces are pointed towards the center of the circle. The force, both when we're talking about when it was up here in the orange form or when it was down here in the yellow form, that force that makes it move in a circle is called a centripetal force. So thanks for watching this video. There'll be more about an equation associated with this in our next video. So hang in there and we'll be together soon.